Hello everyone. This presentation is going to be the first of two on an area within AI that's having a lot of impact on the way material science is performed, and that is computer vision. So the one overall theme that I want you guys to understand from computer vision is that this is a field that is extremely well studied. This is an example from a blog post in 2020, just illustrating the richness with which AI-based computer vision techniques can go and really understand what information is available in an image. And here you can see an image that is segmented into vehicles. There are pedestrians and street signs, and there are plenty of techniques within computer vision, even outside of the AI sphere, that can tell you what is the estimated position and velocity of these different images within a movie, just as an example. And the other bit to understand is this kind of modern adaptation of computer vision with AI-based techniques is built on a very rich history. And I think the Postal Service is actually a great way to understand this. The stamp on the top left of this slide is from the 1970s in the Soviet Union that was illustrating that they already back then had electronic-based ways of reading the a zip code, or I guess the Soviet equivalent of the zip code, off of an envelope. And even 30 years ago in the 1990s, the United States had techniques that could even read handwriting off of images. And this is showing an excerpt from a newspaper in a semi-rural part of Florida. Volusia County's about an hour from where I grew up. It's not the biggest place that one would expect to see technologies getting rolled out first. It wasn't for these self-reading mail systems. But by 1992, they had a system that would go through and process, let's see, it says 12 envelopes per second of being able to do optical character recognition. And again, this is 30 years ago. And the technology that really unifies all of these different kind of technologies is the notion of filters and how they are applied to images. So to give that example, we'll show a simple kind of filter, a filter that responds to vertical lines in an image, where you can imagine I've got this matrix that has two weights in it that as I take and apply to each step in an image, you can see if I put it at this top left corner of my image, my only non-zero points line up to blank parts in the image, so my impact is 0. But if I have it in the center, they both line up with a vertical point on either side, and I get a very strong response. And you can see that with this simple example, if I apply this filter over an image, I can see that the ones with vertical lines get a strong response, and that gives me a very easy kind of classifier. Those which respond well to this filter have vertical lines in them, otherwise they don't. And this is a very simple mathematical technique, and you can use it for a lot of kinds of applications. You can imagine building more complicated filters for, say, face detection, and this is a common technique where that kind of filter will, say, detect having a dark line on top of a light one within the center of an image that kind of picks up where someone's eyebrows might be, or having one with a light portion towards the center, darker on the sides, which you might guess by its position would respond to something like eyes in an image. But there are all other kinds of techniques you can use for these filters besides just image classification. I can determine where edges are in an image and, say, skeletonize it using a edge filter, where here my filter responds to when I have a strong difference on either side of a vertical axis. This, if you're kind of coming from a computer science background, you can also think of as a numerical derivative, where I'm taking the difference of points on either side of a target space, such that you can see how when I raster it over this filter, it gives me a strong response. exactly where the edge is located. There are even sophisticated techniques like sharpening images, where if I can come up with what the point spread function that describes how an image was blurred, I can then take that filter, invert it, and then use that to create, say, a sharper image by, say, correcting for the effect of atmosphere on a telescope image. And this is something that people have been doing for decades. I think the original technology for this kind of thing was actually invented in the 40s. So it's something that, while built on mathematical strong foundations, it consequently hasn't gone out of date. And you can take a look at the convolutional neural networks, which are the ways we go about learning these filters from data. If I look at the Keras documentation, you'll see the word filter placed prominently. And the idea with these convolutional neural networks is you come up with filters that are convolved across images. Convolution is that process I showed you of how we're rastering this filter over different parts of the image. And deep learning lets you come up with things like this, which this is a filter used as part of a image classifier. That would be something by far more complicated than what humans would come up with, but as illustrated by the performance of the network, does quite well when trained for a specific task. And those tasks, when we're looking at materials science, can be a lot of different things. And we're going to show you a few of these different examples that range between, say, predicting the property of an image with classification or regression, through surrogates to make image processing techniques faster, and these are some we're going to go into and some of the practical assignments that will go along with this lecture. Performing microstructure generation, where I say create a bunch of photographs that look like a certain microstructure so I can derive statistics. I can simulate many different equivalent materials even if I only have the ability to actually measure one. Or denoising. So these I specifically chose to sample a different levels of complexity for using this basic notion of convolutional filters in neural networks. And we'll start off with one type that's relatively simple. Building a regression model where I take an image and I want to map it to some continuous property. And one example of where this has been done in science is determining the angles from a backscatter diffraction pattern. So in short, backscatter diffraction is a microscopy technique where I measure how electrons, if I shoot them into a material, reflect back out of it. And the interesting part about crystalline materials is the way that they get reflected back out of the materials is defined by where these crystallographic planes are that say define the common kind of corridors and tunnels that one finds in a material that has a repeating pattern. And we can figure out where these, be able to generate what these maps, which are called Kikuchi maps, are by knowing what the structure is. And if I can take an image like what's shown on this detector here, I can back out where on this map that image came from, and I can repeat that process for many different pixels in a microscopy sample, and I can use that to study, say, how the rotation angle of these little grains within a larger crystal are, and that, from the purposes of materials science, can be used to tell a lot about how this material will behave. Now, the computational challenge in this is that the way one conventionally does this EBSD mapping, where I'm taking these patterns, using them to determine the angle of that part of the material, is by doing a big lookup process. I'll generate a lot of images by knowing what my crystal looks like, and then I'll match my observed image one by one to each of these, which can take a long time, because if I want a high degree of accuracy in this measurement, I need to generate a lot of images to form a library. And one way that we can go about speeding this up is, instead of using what is in effect a very simple machine learning model, a first nearest neighbors classification or regression model, we can try to do something better and faster with convolutional networks. So here I can take my friendly neighborhood CNN, where I've got these notions of filters that I periodically apply to an image until I've created enough responses to those filters that I can map them to some property of interest. And the way that this works for mapping a backscatter diffraction pattern to the angles that define how it's oriented compared to the incoming electron beam can follow one of these very simple sort of apply filters continuously until I can apply them through a conventional neural network that can predict my outputs. Now, I didn't mean to oversimplify this particular work, though I did choose it because of its relative architectural simplicity, such that I could take a neural network from Wikipedia, and that could be sufficient for describing how it works. There were a lot of interesting scientific advances that went on in being able to make this work, such as taking into effect that I'm predicting an angle of 360 degrees and 0 are the same, so I need to build a loss function that reflects that periodicity, and they invented this cosine loss function, which takes that periodicity into account. So moving into something slightly more complicated, we'll talk about defect detection. And this is something that's really useful in material science because many different areas of materials engineering involve looking at micrographs and quantifying the different features that you find in them, such as this image here, which shows what happens to an iron-nickel alloy after we expose it to radiation, and measuring the properties of a specific kind of pattern within here. They're looking at these ellipsoidal types of dislocation loops. The material science isn't too important, but the practical notion of turning this into an image classification problem is there are a lot of other defects that look like this in microscopy. Even the fact of finding a loop doesn't mean that you found the correct type. So in order to be able to do this automatically and not by having a scientist sit at a workstation and spend hours upon hours quantifying the presence of these defects so we can study how well that material handles under radiation, a group at the University of Wisconsin came up with a multi-stage machine learning approach for doing this. So the first two stages are machine learning based computer vision. I have a technique for taking an input image and identifying where I have interesting features that are probably the kind of dislocation loop I'm looking for. And then they pass those regions of interest through a more sophisticated convolutional neural network model that filters out the ones that are close but are not quite the technique that we're looking for. And once I have these loops identified, there's some conventional image processing that I can do to say start with the darkest pixel and then fill outwards such that I can identify where my regions of the loop are in that image. And then I can do some analysis to say quantify the center of that loop such that I can measure their density and diameter and get all of those great kinds of quantitative data that would have taken a human a long time to do. So we're going to break this multi-stage pipeline down into the two of the machine learning parts. So the first step is the way that we take this input image and put a box around each of the features that we think are interesting. And the way that this is done is using a technique known as sliding window region identification. So what this does is you take a region of interest of a certain size and you raster that over the image until you find each of the ways you can place that box such that it gives you a very high prediction of that specific region being the type of feature that you're looking for. Eventually, you get a bunch of these different regions that say are slight perturbations of the actual best match. And I use a process that's well defined from computer vision to merge these many possible maps that are all duplicates of the same feature into one that describes them all best, such as taking all of these slightly offset pictures of a face and detecting where kind of the best representation of that face within our image is. The next part about this that you may be wondering is, well, how do I get these my classification of that region. And the way I do that is I generate a lot of images of actual features that I'm looking for, like my particular dislocation loop or a face within a photograph. I get a bunch of negative images that can be anything else from the type of photograph that I'm looking at. So I can take other kinds of defects, or I can just take a random space. And then I generate a lot more training examples through augmentation, where say I take that feature and I apply transformations to it that make it actually the same feature. Like if I take a dislocation loop and I rotate it, it's still a dislocation loop. Or if I take it and I simulate taking that image under a darker contrast, that's still a dislocation loop. So that gives me a ton of training examples that are positive, and I can easily generate more negative ones by, say, taking regions that are not my dislocation loop and randomly picking different subsets from them. The way that this particular paper built a classification model using all those examples was using a very simple technique called a cascade filter, where I build machine learning models that pick a few sets of features or filters from an image to use as features for the input. So say it could take the response of a filter that is effectively an eyebrow detector or a nose detector and use that as a way of judging whether this image is the desired feature or not. And the way that this works to make it very fast is I build a lot of these different classifiers, and I use a technique called AdaBoost to be able to combine their predictions into a single model. And I perform a process when I'm running inference on this model that I use my models up front to say quickly reject an image as not a face or not a defect, such that I don't actually have to evaluate the entire chain of models. I can truncate it early if I've received, say, enough false classifications that I'm really sure this is not an image. And that what makes it possible to do this rastering technique where I'm applying this machine learning model over and over again in an efficient way. So once I have that, I have a next task of being able to take these images that are already identified as probably a dislocation loop based on the simple machine learning model, and now I want to go through and identify whether these images are truly a dislocation loop at a much higher fidelity. So I'm going to use the same kind of machine learning model where I apply a bunch of different filters through a convolutional neural network. I take the responses of those successive series of filters to create features for a neural network model. And the way that they trained a classification model was to generate 3 different samples of each image. For one, I took it originally as taken. I have another one where I blur it, and a third where I saturate it. Probably not to the extent that I've shown here for a cartoon example, but it gives me another picture of what this feature looks like. And this are able to train a model that could kind of achieve classification accuracy that was comparable to a human rater and at a much faster cost. Their machine learning model only took 30 seconds for each image rather than, I think, the 10 or 15 minutes it took a human in the paper. And a couple other things to point out about this is some of the other kind of neat findings they had in the paper. So one thing they made sure to do when training was they used different levels of magnification, different dwell times, which controls the contrast of the image, or different resolutions of the detector, to make sure that their machine learning model wasn't going to memorize how to do really well under only a certain imaging condition. And this, I think, is a great example in the literature of how someone considered the bias in their training data and took methods to try to counteract it. Additionally, I'll point out that training that initial cascade object detector took 6 days. So this is still a very expensive machine learning model to train. And 30 seconds is still a very slow process for an image detector. Now, you can imagine if this were in a car, having 30 seconds to be able to identify a pedestrian in an image would be far too long to be able to take any action about how to say, control the driving of the vehicle or not. So there are some later methods that build in a faster method for region proposals where you don't have to raster that classifier over the entire image. And you might recognize these as techniques like YOLO, which stands for you only look once, which is reflecting the fact that you don't run that classifier over the same image more than one time. So with that taken care of, we'll move into kind of a final example of how one can use machine learning models in science, or image-based machine learning models in science, and talk about coherent diffraction imaging. So coherent diffraction imaging takes a particular kind of signal that you get when you shine an X-ray onto a sample that reflects how the crystal fields within that particle diffract data. And there's a technique you can use to be able to reconstruct what that sample looked like by applying this iterative so-called phase retrieval process from the image. And if you can go through this entire process, you can actually go through and figure out where there's actually strain within that crystal. That can tell you all kinds of great things about catalysis and how nanoparticles form. But it's a very expensive technique. That process is iterative. You have to repeat it many times, and each of those iterations is not particularly fast. So if you want to be able to do this quickly to say, check if your imaging conditions are good enough to give you a good image of that strain field without having to wait an hour for the image to develop, or you want to record a lot of data using this techniques, like if you want to image a movie of a dynamic process, you really need something faster. And that's if we can, of course, recast into a machine learning problem. I have some unknown function where I can produce inputs and outputs to it. So perhaps I can use supervised learning to be able to create a machine learning model that would do that for me. And as you might infer from the lecture, convolutional neural networks are a great choice for being able to do this. And the architecture that Matthew Chiricahua and others came up with follows this kind of decoder-encoder pattern, where my encoder uses convolutional layers to be able to condense information from an image. It's learning those features, which I can combine down to really capture the essence of what this pattern holds. And then I have two different kinds of decoder networks. The first of which generates the amplitude, which is a picture of just effectively the density of the material and how much it scatters. And the second retrieves the phase, which again holds that information like strain. And the way that it does this is also with convolutions. Now, I showed you earlier how if we can learn, say, the source of a blurring pattern on an image, I can actually go back and effectively kind of add more information to the image that was lost by blurring. The decoders in this network work in a very similar way. They take those essences of that diffraction image and be able to build back the information that wasn't available in that original image, so we would have had to spend a lot of time with knowledge of the physics to recreate. We can go through and effectively learn that physics through the network to be able to retrieve those phase and amplitude without ever doing any of the phase retrieval through that physics-based method. So hopefully these three examples and that introduction give you a real perspective on where artificial or computer vision, especially that through artificial intelligence, can play a role in materials engineering. And really the things I want you to take home is filters are at the bottom of basically all of these techniques, where these filters capture different ways of extracting information from an image or being able to add more information to it based on some knowledge of how that image was created. And you can be able to learn these sorts of filters based on convolutional neural networks, which learn those filters from the data. And hopefully through these three different examples, I've been able to show you a few different ways that we can use very simple convolutional networks trained with supervised learning to do some rather complicated tasks, like being able to identify which, or from this Kikuchi map, what part of a crystal or what orientation I'm actually looking at. So that wraps up all we're going to talk about convolutional networks today. Our next lecture will be focusing on how we can train them with more complicated methods like adversarial training, and we can use that for things like denoising.